Hello everyone. This video is on the Knewton Alta assignment for section 7.4 called Factoring Special Products. In this video I'm going to be going over a preview version of this assignment, so please understand that the questions I see in this video may not be the same questions that you see when you work on the assignment yourself. Pardon me. But the objectives are all the same, the structure should be similar, so I'm hoping that watching me do these here helps you out in some way when you work on the assignment on your own. Now on the assignment page you should see the title, the mastery bar telling you how far along you've gotten, the objectives. It looks like there are 3 objectives for this assignment. And then under the current objective there should be a question related to that objective. And at the bottom of every question you should see a feedback button where you can send feedback to Knewton if you wish. You will not have this instructor cheat button, right? It's for instructors only. But you will have a more instruction button, right? This is if you're struggling with a topic or a question, click on this and you'll be taken to a page with some reading or videos to study, and then you'll be given questions related to that instruction, and completing those questions is another way to progress through the assignment. Alright, so the first objective I'm looking at is factor sums and differences of cubes. Alright, so these are very special polynomials with 2 terms, very special binomials that you'll be able to factor. Right. So first I'll talk about a sum of cubes, and then factoring a difference of cubes is very similar. So a sum of cubes is a special kind of binomial where you have some expression cubed, right, some expression to the 3rd power, plus, and then some other expression to the 3rd power, right? It's a cube plus a cube, right? A sum of cubes. Now, if you recognize an expression as a sum of cubes, you should be able to factor it, write it as a product of 2 factors. The first factor is simple. The first factor you write, just get rid of the cubes. Right, so the first factor is just going to be a plus b times, and then the second factor is going to be a trinomial, right, something with 3 terms. And it's actually going to be a quadratic, a degree 2 trinomial. And just think a little bit. If I have a here in this first factor, what would I need to multiply it by to get a cubed? Well, that would be a squared, right? So the first term in this second factor is a squared. And then what I like to do is in this trinomial, right, so I'll close the parentheses over here, we have a trinomial. The power of a decreases by 1 each term. So the first term of the trinomial factor is going to have a squared. The second term is going to have just a to the first. And the third term has a to the 0, which is just 1. Right? So no a at all. And in fact, that third term needs to be b squared. Right? Positive b squared to get b cubed when you multiply, right? You'll distribute the a, then you'll distribute the b. You need this last term to be positive b squared to have the positive b cubed from the original expression. And then kind of reverse what I did with the a's. The power of b decreases as you go from right to left. So there's b squared in this last term, a factor of b to the first in the middle term, and then no b at all in the first term. And then The only thing I need to fill in now is the sign of this second term. If there's a plus here, if this is a plus b, this sign is the opposite, minus. All right. And I'll make that little note. And in fact, there's a little acronym that you may read about in certain texts that relate to the signs involved in this sum of cubes factorization formula. So like in this first factor, you have a plus b. That's the same sign as this over here, right? If this was a sum of cubes, this is the same. It's a sum in this first factor. And then this sign here between the first two terms of the trinomial factor is the opposite sign. Opposite. Right? If there's a like I said, if there's a plus here, there's going to be a minus there. And then this last term, right, the third term in the trinomial factor, has to be a positive b squared. It has to be plus b squared. This is always plus. Always plus. Always positive. So the acronym here is SOAP, SOAP. You know, wash your hands with soap or whatever. I have seen that written out in some texts, and I find that some students do have an easy time remembering that. Same, opposite, always plus, or always positive. The hard thing I find students have remembering is how this trinomial factor is structured. So remember the first factor, just get rid of the cubes, a plus b, and then the second factor has a squared, and then the power of a decreases. And then you could also think of no b, and then the power of b increases as you go from left to right until you get to b squared plus b squared in the end. And if you wanted to check, of course, you could multiply these, right? You know, a times a squared is a cubed. A times negative ab would be negative a squared b. And then a times b squared would be positive ab squared. And then distributing the b's, you have positive a squared b, but that gets rid of the negative a squared b from earlier. And then b times negative ab would be negative ab squared. That gets rid of the positive ab squared from earlier, so those are all canceling. And then b times b squared is b cubed, and I end up with a cubed plus b cubed after combining like terms. I know that was kind of said pretty quickly there, but you can check your factoring by multiplying. And then you'll see that a difference of cubes is very, very similar. Right, the only thing that changes are some signs, some pluses and minuses. Right. So a difference of cubes is another special binomial where you have some expression, you know, cubed, some expression to the third power, minus, right, it's a difference minus some expression to the third power. And if you recognize a binomial as a difference of cubes, you should be able to factor it, write it as a product. And it's the same setup where it's a binomial factor times a trinomial factor. That binomial factor is once again very simple. Just get rid of the cubes. The first factor will be a minus b, which in that SOAP acronym, right, has the same sign as your difference. If it's a difference of cubes, this is a minus, right? Same sign. Times, and then the trinomial factor is set up the exact same way. A squared in the first term, a to the first in the second term, no a in the third term, no b in the first term, b in the second term, and then again plus b squared for that third term, so that way when I distribute the negative b, I get my minus b cubed. So there's your always plus, right? Always plus the AP in the SOAP. And then the opposite sign is a plus here, right? A squared plus AB plus b squared. And again, that's the opposite sign of the minus here. If there's a minus here, there's a plus there. And again, you can check by multiplying. Multiply these out, combine like terms, you will end up with a cubed minus b cubed, I promise you. Alright, so our first example is a sum of cubes. All right, our first example is a binomial. All right, we have 125 m cubed plus 1. Right, and we're asked to factor this if we can. Right. Now, again, I know I only put up this next to the sum of cubes because it is a sum, right? If this was a minus, I would think it was a difference of cubes, and I'm also noticing a third power here. That's what's making me think it's going to be a sum of cubes. But now I have to rewrite this so that it is indeed a sum of two cubes, right? This is not all to the third power here. This is, m is to the third power, but not the 125, right? So it's not a cube yet. But the nice thing is 125 is a cube. It's 5 cubed. So I can rewrite this first term as 5m to the third power. 5m times 5m times 5m is 125m cubed. So there's a cube, something all to the third power. Plus, and then 1 is, obviously a cube. It's 1 cubed. So I do have a sum of cubes here. And now I'm just going to go through my little formula. Right? If you have, I would highly recommend you memorize these. All right. It's probably the only way you're going to be able to do these sums of cubes and difference of cubes and do them quickly. So again, going through the formula here, I'm just going to replace every single a with 5m. Right? That's the capital A in my formula is going to be this 5m. And I'm going to replace all the capital B's up here with 1. So again, the first factor is a binomial. Just get rid of the cubes. It's going to be 5m plus 1. Right? 5m plus 1 times, and then a squared. So again, when you replace something, put it in parentheses. Right? That's a 5m squared minus a times b 5m times 1. Then always plus, and then b squared, 1 squared, right? I'm just replacing all the capital A's with 5m, all the capital B's with 1. And then of course we simplify. 5m plus 1 for the binomial factor. And then 5m to the second power is 25m squared. Minus, 5m times 1 is just 5m. And then 1 squared is just 1, so plus 1. And here we go, and this is what they want us to do, right? This is it. There's your factorization. Right. Now, of course, you should always look for the greatest common factor first, but the greatest common factor is 1 here. I didn't mention that, but I have mentioned that in sections, 7.3 and 7.2 and 7.1, right? So you should know to look for the greatest common factor first. And then you might ask yourself, well, hey, what about this? What about this 25m squared minus 5m plus 1? That looks like one of them special trinomials, ax squared plus bx plus c, Well, I'll tell you right now that this is going to be prime. All right, that trinomial fact. If you've already pulled out the GCF and then you got a sum of cubes and you factor that sum of cubes, I'll tell you right now the trinomial factor won't be able to be factored anymore, so I'm not going to bother with it. And you shouldn't either. And there we go. And then again, check by multiplying. All right, check by multiplying. Make sure that this product is equal to 125m cubed plus 1. Now, I'm assuming you remember how to multiply polynomials. All right, so I'm going to do that here. So I would distribute the 5m plus 1 to these three terms and then distribute that. So basically, these two terms get multiplied by all three of these terms, and then we add up like terms. So first I'll distribute the 5m. 5m times 25m squared, that's 125m cubed. 5m times negative 5m would be minus 25m squared. 5m times 1 is positive 5m. Alright, so now I'm done with the 5m. Move over to the 1. Distribute the 1 to these three terms. 1 times 25m squared is plus 25m squared. 1 times negative 5m is negative 5m. 1 times 1 is 1. And then combine like terms, we get 125m cubed. And then you see that the m squared terms cancel. They're, negative 25 plus 25, that's 0. And then same thing with the m to the first terms. 5m minus 5m is 0. And then I'm left with plus 1. And that's exactly what I started with. 125m cubed plus 1. So this is the proper factorization. This is the correct factorization of that polynomial. So 125m cubed plus 1 will factor to 5m plus 1 times the trinomial 25m squared minus 5m plus 1. And that should be good. And again, you can put these in either order, but usually I like putting the binomial factor than the trinomial factor. I find it easier to remember. But it's up to you. And then after you submit an answer, you'll be told whether you're correct or incorrect, and then given some sort of answer explanation. Right. Please read through the answer explanations just to make sure you understand where you went wrong or why something was right or wrong, and hopefully you can learn from your mistakes for future questions. Alright, so now we're working with these perfect square trinomials. Factor a perfect square trinomial. Now you've seen these before, right? You have. It was in when you were learning how to multiply polynomials, there was a section about special products from chapter 6, I believe. I forget exactly what section, but let me write that out here. We'll come back to the sum and difference of cubes, but perfect square trinomials are just the squares of binomials. So remember earlier, again, you take a binomial, say a plus b, and you square it. Remember that would be a plus b times a plus b again. And this ended up being a squared plus 2ab plus b squared. Well, this is a trinomial that ended up coming from the square of something. So that's called a perfect square trinomial. Right, so this expression here is an example of what's called a perfect square trinomial. Something with three terms that is just a square. That can be written as a square. So what we're going to be doing is going in the direction right to left. All right, so what I'm doing is I'm going this way. We're going to start with a trinomial and hopefully recognize it as a perfect square trinomial. The first term is a square, the last term is a square, and the middle term is twice the product of their square roots. If you recognize that, then you can jump right to the saying, oh, this is going to be a, this squared here, right? Some binomial squared. There was also the a minus b, right? If you squared a minus b times a minus b, that ended up giving you a squared minus 2ab plus b squared. All right, but again, this is another example of a perfect square trinomial. Three terms that can be factored as the same factor twice. Can be written as a square. All right, so this is what we're working with now. So the example I'm given here, and they're kind of telling you, that it's a perfect square trinomial. We have a 64 q squared plus 112 times q, and then plus 49. This is actually that first form we'll see But we have to see it though, right? You can't just say, oh, this is 3 terms, it's going to be one of these. That's not necessarily the case. 64q squared, that's a square. That's 8q to the second power. So the a here is like this 8q, right? It's a squared. The last term, right? Usually I check the first and last term to make sure they're squares, right? A squared and b squared. 49 is, 7 squared. So the first term is a square, 8q squared. The last term is a square, 7 squared. Now, in order for it to be a perfect square trinomial, the middle term has to be twice the product of their square roots. So is the middle term 2 times 8q times 7? Well, 8q times 7 is 56q times 2 would be 112. So this is a perfect square trinomial. It checks out. It has this form where a, right, a is the 8q. There's a again, right? And then b is the 7. Right? It's a squared plus 2ab plus b squared, exactly like the right side up here. So this should be able to factor, and it'll factor to the same factor twice. It's going to be a plus b, that quantity squared, and a is 8q plus, and then b is 7. And here we go. And again, you can check by multiplying. Take 8q plus 7 and multiply it by 8q plus 7 again. Do all the foiling and whatnot, all the distributing, and you'll get 64q squared plus 112q plus 49, I promise you. Right? And I'll leave that to you this time. And that's all we're doing for these, right? Just recognizing that we have a perfect square trinomial, something of one of those forms, and then factoring it, writing it as the same factor twice. So 8q plus 7, and then you can write, you should be able to write 8q plus 7 times 8q plus 7, but usually when the same factor appears twice, we just write squared, right? Write it to a power. Great, and that should be the case for all these perfect square trinomials. Right? You should be able to write it as, some binomial to the second power. All right, so here's another one with a perfect square trinomial. So, same page. So again, we're going to be given something that's in one of these forms on the right side here of the equal signs. So we have 4u squared x. Oh, okay, so this one I'm going to have to pull out a GCF. Remember that's the first step in any factoring. Plus 16 times ux squared, and then plus 16x cubed. All right, so remember the first step in anything, the last problem didn't have any GCF, other than one. The greatest common factor here, if you look at all three of these terms, clearly 4 times x is in all of them, is a factor of all of them. So I pull that out first, and then we'll look at the trinomial left over. If I pull out 4x, we'll have u squared plus 4ux plus 4x squared, right? And this factor left over after pulling out the GCF, this should be a perfect square trinomial. And we'll see that in a second. Right, and I'll do this off to the side because you got u squared, right? So the u is like the a. The last term, 4x squared, is 2x to the second. So 2x is like the b from my formula here. And then the middle term, again, if the first term's a square and the last term's a square, in order for it to be a perfect square trinomial, that middle term has to be twice the product of their square roots. So is the middle term 2 times u times 2x? And yes, it is. 2 times u times 2x would be 4ux. So this will factor, right? We have the GCF we pulled out earlier, 4x, And then this u squared plus 4ux plus 4x squared will factor to u plus 2x squared, right? U plus 2x times u plus 2x, or the quantity u plus 2x to the second power. Great, but yeah, that pulling out the GCF though, that is always the first step in factoring anything. So 4x times the quantity u plus 2x to the second power. Or you could write u plus 2x times u plus 2x again, nothing wrong with that. But like I said though, usually when there's the same factor twice, you put a square. Right? Alright, so back to sums and differences of cubes. Here I got a minus sign, so I'm probably going to be dealing with a difference of cubes eventually. Alright, so let me bring that page back with the difference of cubes on it. Alright, but this time again, you got to pull out a GCF first. You know, this is 27 times m times w cubed minus, and then 64m. The greatest common factor of these two terms is m. Alright. Because 64 and 27 don't have any common factors. So I'm just going to pull m out first. And then if I remove the m, then we have 27w cubed minus 64. And this, right, this factor left over in the parentheses here, this is going to be a difference of cubes. All right, and I'll show you off to the side. You know, 27w cubed, that's 3w to the third power. There's how it looks as a cube. Minus, and then 64 is 4 cubed. 4 to the third power. So in my formula up here, right, the 3w is like the capital A, and 4 is like the capital B, right? So this will factor to 3w minus 4, right? Just get rid of the cubes for the binomial factor. And then for that trinomial factor, yeah, we got a squared, right? So 3w squared plus ab, so plus 3w times 4, and then always plus b squared or 4 squared, and we'll simplify that. All right, so I have m, right, the GCF that I pulled out, times, and then this difference of cubes factors like this, 3w minus 4 times, you know, 3w to the second power is 9w squared, plus 3w times 4 is 12w, and then plus 4 squared is 16, right, plus 16, and there we go. This is as factored as that polynomial is going to get. And again, you can check by multiplying, but I'll leave that to you. Right, so the GCF m come out, and then the difference of cubes factored to 3w minus 4 times 9w squared plus 12w plus 16. And that should be good here. Great. Alright, now the last of the special products here, the last of the special factoring formulas is factoring a difference of squares. And this is another one you have seen. It's just, you know, when we were learning how to multiply polynomials, there was a section on multiplying conjugates. And when you multiplied two conjugates, you ended up with a difference of squares. So this is just reversing that. Right, this is going to be just reversing that to factor. So a difference of squares, difference of two. This is another special binomial. All right, kind of like a sum of cubes and a difference of cubes are special binomials, things with two terms. All right, a difference of squares. Again, I'll write it the way we remember. Remember, if you take two conjugates, a plus b times a minus b, remember these were called conjugates, a plus b, a minus b, a minus b, a plus b. If you multiplied two conjugates, you ended up with a squared minus b squared, right? And this expression here on the right side, this is what they call a difference of squares. All right, there's a square minus a square, a difference of squares. So what we're doing here is just going in this direction. All right, I'm going to be given something that's a difference of squares and asked to factor it. And the difference of squares is just a product of two binomial conjugates. It'll be a minus b. Again, just one of the factors is just get rid of the squares, a minus b, and the other factor is just its conjugate, a plus b. Right. So this should be a simple one. Now be careful. One note I want to make here is that, yes, there's a difference of squares factoring formula. There is no sum of squares formula. Okay, there is no sum of squares formula. If you see a squared, plus b squared, if no GCF, if the GCF is 1, then it's prime. You would just not factor it at all, okay? If you can't pull out a common factor, then it's prime. Now there might be sum of squares that are also sums of cubes, like if the powers were to the 6th power or something, or some multiple of 2 and 3. Then instead of looking at it as a sum of squares, you'd look at it as a sum of cubes, and then you'd be able to factor it. So I guess if the GCF is 1 and it's not a sum of cubes, then you're going to say it's prime. All right. So I'll add that little note. If the greatest common factor is 1 and it's not a sum of cubes as well. All right. So sums of squares don't factor for the most part. Differences of squares do. You get a product of conjugates. So the first example we're given here, and again, that's probably something we're going to have to pull a common factor out of first. We have 125, which is not a nice square. That's actually 5 cubed. So we're going to have to pull something out here. Times c squared minus 80, which is another thing that's not a nice perfect square, times z squared. Well, I do notice that the greatest common factor of these two terms is 5, right? This is 5 times 25, and 80 is 5 times 16. So I'm going to factor the 5 out first, and then, the factor left over, the binomial left over, would be 25c squared minus 16z squared. And it's this binomial that's a difference of squares, and I'll show you how. This is a difference of squares. So I'll take this over here. 25c squared is actually the same thing as a 5c to the 2nd power. Right? There it is as a square. Minus, and then 16z squared is the same thing as 4z to the 2nd power. So this 5c is like the capital A from my formula, and the 4z is like the capital B from my formula. Right? So this would factor to, just again, just get rid of the squares. 5c minus 4z times its conjugate, 5c plus 4z. And there we go. But don't forget the factor of 5 though, right? So the 5 I pulled out, so we still have that factor. And then this 25c squared minus 16z squared, difference of squares, factors to 5c minus 4z times 5c plus 4z, or 5c plus 4z times 5c minus 4z, right? Remember, it doesn't matter what order the factors come in. But There we go. That's what I'm going to type in. And again, you can check by multiplying. See that you get the original expression back, and you should. So 5 was the GCF, and then the difference of squares factored to 5c minus 4z times 5c plus 4z. That should be good. Great. Alright, so now we've seen all the formulas. Sum of cubes, difference of squares. No sum of squares. Be aware of that. And then you have those perfect square trinomials as well. Alright, so here another difference of squares thing where once again I'm going to have to pull out a greatest common factor first. So let me do this one more time here with the formula up. So we're given 32a squared plus 50q squared. And look, this is a sum. The only way I'm going to be able to factor this is if it's a sum of cubes, or if it has a greatest common factor that's not 1. Well, there are no cubes here. These are squares. But I do notice that there is a greatest common factor, though, that's not 1. 32 and 50 both have a common factor of 2. So I can at least factor that out. So this is 2 times 16a squared plus 25q squared, and that's it. That is all I can do. All right, here is a sum of squares, right? This is a sum of squares, and I already pulled out the GCF, and it's not a sum of cubes, right? It's not a sum of cubes. So can't factor anymore. I can't factor this. This is as factored as it gets. That's all I'm doing, is pulling out the 2. Now if that was a minus, then I could factor it. All right, but it's not. It's a sum of squares, not a difference of squares. So all I can do is factor out the 2. And then we have 2 times 16a squared plus 25q squared, and close the parentheses there. That's it. And they even mention here, right, a sum of squares does not factor. Again, as long as you've already pulled out the greatest common factor, and it's also not a sum of cubes, but they don't go into all that. All right. So another thing with a possible difference of squares. So once again, I'll keep the difference of squares formula page up. There it is. And here we're given 49d squared times n minus 25n. First thing always is to find a greatest common factor. This time it's not 1, it's n. They both have n in common. I factor that out. And then what's left over will be a difference of squares. 49d squared minus 25, which is the same thing as 7d to the second power, right? There's your first square, minus, and then 25 is 5 squared. All right, so that factors, we have n, right, the GCF that we pulled out, and this 49d squared minus 25, that's 7d to the second minus 5 to the second. This will factor to 7d minus 5, right? One factor is just get rid of the squares, and then the other factor is the conjugate, 7d plus 5. And here we go. N times 7d minus 5 times 7d plus 5, or put those factors in whatever order you want. So n times 7d minus 5 times 7d plus 5. Great. All right. Still with a possible difference of squares. Now I'm already telling you, it says factor if possible. See, it's 25 plus 64w squared. This is 5 squared. This is 8w to the second, right? 25 and 64 don't have any common factors other than 1. This is a sum of squares, not a difference of squares. So this cannot be factored at all. There's not even a greatest common factor to pull out. So this is it. That's as factored as it gets, 25 plus 64w squared. That's as much as you can't do anything with it. And it says if it can't be factored, just enter it in its current form. Yeah. So just be aware. Now if that were 25 minus 64w squared, then I could factor it to 5 minus 8w times 5 plus 8w. But it wasn't a difference of squares though, so just be careful. All right, so now we're back to the perfect square trinomial formulas, right? Those two forms. I'll bring that page back. So here are the perfect square trinomials. Right. Again, we'll try to find things that look like one of these two forms. This one does have a minus in the second term, so I'm probably going to be using the second form here with the a minus b squared. So we have 2u squared v minus 20 uv squared plus 50v cubed. Well, just as with anything else, the first thing you should look for is do all the terms have some common factor I can pull out? What's the GCF? And here that would be 2v. So I factor out 2v first, and if I do that, the factor remaining would be u squared minus 10uv then plus 25v squared. Alright, and I'm hoping you can see that u squared is, u squared, so a is u. 25v squared is actually 5v to the second, so b is 5v, and then the middle term is minus 2 times u times 5v, right? That'd be minus 10v. So this is one of them perfect square trinomials where capital A is u and capital B is 5v. So that would factor to u minus 5v times u minus 5v again, right? So the quantity u minus 5v squared. There we go. And that's as factored as that's getting. So the GCF 2v out first times, and then that perfect square trinomial factored to u minus 5v, to the second power. Okay. Alright, so one more of these with a perfect square trinomial. So keeping the same page up. Now again, the way it starts doesn't look like a perfect square trinomial, but when I factor out the GCF, then the trinomial left over will be a perfect square trinomial. So I have 18 u squared v, pardon me, minus 12 uv squared plus 2v cubed. All right, the greatest common factor of all these terms is just 2v. So I pull out 2v, and then what's left over is 9u squared minus 6uv plus v squared. Alright, so this is going to be a perfect square trinomial here. Look at 9u squared is 3u to the second power, so a is 3u. V squared, so b is v, and the middle term is minus 2 times ab, 2 times 3u times v. That's minus 6uv. So 2v times, and then this will be a minus b squared, where a is 3u and b is v. Right, so that second trinomial here will factor to 3u minus v times 3u minus v again, or the quantity 3u minus v squared. All right, so 2v got pulled out. times, and then the perfect square trinomial factored to 3u minus v, squared. 3u minus v times 3u minus v again. Great. All right, and the last stuff we should have is either going to be sum involving sums or differences of cubes. So I'll bring that page back. So this has a plus sign in it between the terms, so it's going to be a sum of cubes eventually used here. We have 8u to the fourth plus u to the first. Now these are clearly not cubes. The powers are not multiples of 3. But like with everything else, right, the first step in any factoring is finding the greatest common factor of all the terms and pulling that out, which in this case would be u. So I factor the u out first, and then we have 8u cubed plus 1 left over. And this 8u cubed plus 1, this is a sum of cubes. This is 2u to the third power plus 1 to the third power. And then going through, replacing all the a's with 2u and all the b's with 1, we get the following factors. The first factor is just get rid of the cubes, 2u plus 1. Second factor, the trinomial has 2u squared minus, and then 2u times 1, then always plus, and then 1 squared. And we'll simplify that when I write it again over here. So we have u pulled out, and then this sum of cubes factors to 2u plus 1 times, and then simplifying the trinomial factor here, we have 2u to the second would be 4u squared minus 2u times 1 is 2u, and then plus 1 squared is just 1. And there's how this polynomial will factor completely. So the GCF of u came out times 2u plus 1 times, and then 4u squared minus 2u plus 1. And there we go. Wonderful. And I should have just one more of these with either a sum or a difference of cubes involved. So once again, I'm seeing a plus sign between the two terms, so probably going to involve a sum of cubes, right? So I'll just leave that sum of cubes formula up. So the expression we're given here is 64 cz cubed plus, and then 27 cx cubed. Greatest common factor is c, obviously, so I pull out c, and then the factor left over, the binomial left over, would be 64z cubed plus 27x cubed. But this polynomial here is a sum of cubes. 64z cubed would be 4z to the third power plus, and then 27x cubed would be 3x to the third power, right? So there's your sum of cubes. And I'm just going to go through now and replace all the a's with 4z and all the b's with 3x. So this will factor to 4z plus 3x times, and then 4z to the second minus 4z times 3x, and then plus 3x to the second. And we'll simplify that when I write it again over here. So we had the c pulled out, that was the greatest common factor. And then this sum of cubes factors to 4z plus 3x times, and then the other trinomial factor, 4z squared is 16 times z squared minus, and then 4z times 3x would be 12xz or 12zx, whatever. And then plus 3x to the second is 9x squared, right? Plus 9x squared. And there you go. That's what they're asking us for here, the factorization of that. So c times 4z plus 3x times 16z squared minus 12xz or zx, and then plus 9x squared. And that should be good. Excellent. So yeah, so you had those, 5 little formulas to remember. There were 2 different versions of a perfect square trinomial: sum of cubes, difference of cubes, and difference of squares. And just remember, there is no sum of squares formula, and you should have a handle on this. And I highly recommend just memorizing all of them, make things a lot faster for you. And that should be it for this preview version of this assignment. Like I said at the top of the video, the questions I saw here may not be the same questions that you see when you work on the assignment yourself, but the objectives are the same, the structure is similar. So I'm hoping that watching me do these here helps you out in some way when you work on the assignment on your own. And thank you very much for watching.